Let's begin.
Okay, so hi everyone. So I have the pleasure to introduce Lucas Pahl, who will be given the junior talk today. So Luca defended his PhD at University of Rochester in 2019 and is now a postdoc at University of Bonn. So his research focuses on game theory and mathematical economics. And today we'll speak about the finite characterization of perfect equilibrium. The floor is yours.
Thank you, everyone, for coming, and thank you again, the organizers, for inviting me for the talk. This is joint work with Yvonne, who I think is online actually, and Hari Govindan. All right, so so let me start with some basic facts that I hope everyone knows in game theory. So the set of Nash equilibria of a finite game is given by finitely many polynomial equalities and inequalities. And if we're given an actual finite game with n the finite set of players, Sn the pure strategy set for each player, and sigma n the mixed strategy set with Gn the payoff functions, it's not hard for us to write down what this set of polynomial inequalities and inequalities are, right? So the first set here in red of inequalities is the set of inequalities that pins down best replies, and the second set of equalities and inequalities defines the strategy set. So with these two sets of inequalities, we can identify the set of Nash equilibria in a game. So the main question in this paper is it possible to obtain a similar finite characterization for perfect equilibrium? Okay. So let's recall the definition of perfect equilibrium. A mixed profile sigma of a game G is a perfect equilibrium if there exists a sequence of completely mixed strategy profiles converging to sigma, and such that sigma is the best reply against each one of the elements of the sequence, okay? So from this definition, it's not clear whether a finite characterization can really be obtained for perfect equilibrium, right? And this is easy to see because you would have to check for a candidate profile sigma infinitely many times whether sigma is a best reply against each element of this sequence, right? So for each k, you have to check whether sigma is a best reply against sigma k. So as I said, we're after a finite characterization, and the type of result we're going to obtain is as follows. Sigma is a perfect equilibrium of the game if and only if a polynomial system P sigma has a solution. And we're going to provide this system explicitly. So in principle, you'll be able to pick the system. It's given explicitly. You'll be able to, let's say, program the system and check whether the system has a solution. And if it has a solution, sigma is guaranteed to be perfect, all right? And the methods we're going to use to obtain this result, they come from two rather recent results in real algebraic geometry. One is the curve selection lemma, proved by Bazou and Hua in 2018. The curve selection lemma is a classical result, but what Bazou and Hua did was to provide a quantitative version of this curve selection lemma, so actually giving estimates for certain constants that are just known to exist. And the same thing with the Loyasevic inequality of Kurdzika and Spotiedza. So in this paper also, they show that certain estimates for certain quantities on the Loyasevic inequality that are known to exist only, and we're going to use these estimates to prove our theorem, right? I'll be a bit more specific with respect to this later. All right, so let me talk about the main tool that we're going to use to construct this polynomial system, and this tool is lexicographic probability systems. So what is a lexicographic probability system? A lexicographic probability system of order k of player n over the pure strategy set of player n is a tuple of probability distributions over the pure strategy set of player n. Okay, so it's just a vector of probability distributions over the pure strategy set of this player. It is said to have full support if this condition here holds. What this condition means is that just each strategy of player n appears with positive probability in at least one of the elements of these LPS. Okay. Oh, sorry. Yeah. So an LPS profile is an assignment of an LPS for each player. Okay, so nothing new there. And that is the nice thing is that there is a natural interpretation for what an LPS is. And an LPS ho n of the player n can be interpreted as the collection of theories that the opponents of n hold about what n is going to play, right? So ho 0 n is can be seen as the primary theory or the primary conjecture about what n is going to play, ho n a secondary conjecture about what n is going to play, and so on and so forth. And it's also considered that ho 0 n is infinitely more likely to be played by player n than ho 1 n, which is infinitely more likely to be played than ho 2 n, and so on and so forth. So there is a certain hierarchy in this interpretation.
I have a question.
Yeah.
So do you then assume that the different levels of the lexicographic probability system have disjoint supports?
No, no assumption of this kind. No.
Okay. Because then perhaps this interpretation is not so compelling what you say, right? In terms of primary theory, secondary theory, and so on. Because if the supports may overlap, then it's not that these theories are perfectly complementary.
Yeah, yeah. So in this sense, that's fine. Yeah, I'm still introducing the classical definition of it. So, but you're right. There's not going to be this assumption of disjoint supports between them. All right. So let me introduce one more notion. With this definition of lexicographic probability systems, we can generalize the common notion of best reply for finite games and to a notion of lexicographic best reply. So a strategy sigma n is a lexicographic best reply of a certain order to the LPS profile ho if this lexicographic ordering of these vectors here hold. So what are these vectors? You just compute the induced payoffs by the lexicographic profile with respect to sigma n and compare them lexicographically against any other strategy, against the vectors induced by any other strategy. All right, so in words, sigma n does lexicographically better against ho minus n than any other of players n strategies. Okay, and I'm introducing here the definition. Of course, in the paper we do this for n players, for any finite number of players, but this will require a bit more definition about how the other players combine the LPSs of the other players to generate a belief about what players are going to do, and this will complicate notation a little bit. So let's just keep in mind the definition for 2 players. All right, so with this definition, we can also generalize the notion of Nash equilibrium, right, to the notion of lexicographic Nash equilibrium. Given an LPS profile ho of order k, sigma is a lexicographic Nash equilibrium with respect to ho if essentially the first theory or the first conjecture here is correct, right? And sigma n is a lexicographic best reply of order k to ho. Okay. So to make these things a bit more concrete, let me give you an example of how do we use this notion of lexicographic Nash equilibrium to identify perfect equilibrium in finite games, okay? We impose conditions on the LPS in the definition of lexicographic Nash equilibrium. That's to do this. So let's consider here this 2-player game. There are 3 actions for each player. The row player is going to be player 1, and the column player is going to be player 2. MC is a perfect equilibrium, and TL is only a Nash equilibrium, okay? MC is a lexicographic Nash equilibrium with respect to a full support LPS of order 1, right? So these are, let's say, the assumptions that we do in the LPS to obtain our identification of perfect equilibrium, right? And you can see that it is indeed full support. All strategies here appear with positive probability, and it's not hard to check that M is a lexicographic best reply against this LPS, and C is a lexicographic best reply against players 1 LPS, right? But the interesting thing, and simple also to note, is that TL is not a lexicographic Nash equilibrium with respect to any full support LPS of order 1. And this you can see because T is weakly dominated by M here, right, for the role player. So any full support LPS that puts positive probability of CNR of the column player will be such that M is going to do strictly better than T. So T can never be a lexicographic best reply to a full support LPS of order 1, right? All right, so with these definitions, we're ready to state the theorem that we prove in this paper. Just need one more notation, and this notation here is L-ho. Okay, so you can read L-ho as the minimal length for the LPS to have full support. I'll call this length only, right? All right, so the theorem says if G is a finite game, okay, then there exists non-negative integers L and K, such that a strategy profile sigma is a perfect equilibrium of G if and only if there exists an LPS profile ho of order K such that 3 conditions hold. The first one says that ho has full support with the length of this LPS less than L. The second one says that the primary theory is correct, right? As we've seen before in the definition of lexicographic Nash equilibrium. And the third says that sigma n is a best reply of order K against ho. So 2 and 3 are just the properties that characterize lexicographic Nash equilibrium. So, but the real contribution here is that we can actually estimate what those quantities are, right? So you don't have to pay attention to the exact formulas here. This is just for you to see that it's possible to estimate them, but they depend L and K only on the cardinalities of the strategy set of the players and the number of players in this game. Okay.
Lucas, can I ask a question?
Sure.
What does those probability system give you on top of just restricting the players to play actions with some given exponent of epsilon? So each action you play with a given exponent of epsilon, epsilon squared, epsilon to the power 3. You take an equilibrium in this restricted subset of strategies. You take the limit as epsilon goes to 0, and this epsilon and this limit gives you a probability system as you define. So what is the difference among the two approaches?
So it's slightly different. So in the construction that I think you're, let's say, using Mertens' suggestion for constructing proper equilibrium, right? So you restrict the strategy sets in this specific way, and then take limits on the Nash equilibria that you compute in this restricted mixed strategy set. So the intuition here is similar, right? To that. The intuition is similar, but still in this construction, you take limits, right? You're taking a limit, let's say, to compute equilibrium. So this is, I'm not sure if I understood exactly your question, but this type of construction won't give you a finite characterization, won't give you a finite system, right?
Why would it be a finite system?
Because you fix epsilon and compute a Nash equilibrium for the restricted strategy set. Yeah. Then you take epsilon smaller, compute another one. Epsilon smaller, compute another one. Epsilon and then you have a limit, right? The limit gives you a Nash equilibrium of the original game with added restrictions.
Yes, but if you look at the strategies with smaller exponents, then they actually give you a probability system as you define.
All right, I'm not sure if I'm following them, but perhaps we can talk at the end about this.
Okay, sure.
All right, thanks. Yeah.
I also have a question.
Mm-hmm.
So about two-player games, because for two-player games, it is known that a perfect equilibrium is exactly a Nash equilibrium where both strategies are not weakly dominated.
Exactly.
And the strategy is not weakly dominated precisely when it is optimal against a full support strategy of the other player.
Yeah.
So this would suggest that for two-player games, the maximal length that you would need would be 1.
Exactly. So the L and K is 1. So for two-player games, it's the problem is very easy to solve. Okay. So the real thing here is for more players, but you're exactly right. Yeah. And you see, even I can comment even in the next slides, I'll show you some intuition on how do we get about L and K, and you see that this is linked to the geometry of a particular set here. Why is it 1, and so on and so forth. All right. So let me give you some intuition on how to find L. So let's start with some sigma that is not completely mixed. Of course, perfect equilibrium of the finite game G, right? If it is completely mixed, we just have to check Nash equilibrium, the Nash condition, right? So let's consider the set of completely mixed strategies such that sigma is the best reply against them, okay? And that's exactly the set here defined by this formula. And this set is non-empty, of course, because we're assuming that sigma is perfect. So there is a completely mixed sequence that is converging to sigma, okay? And to go back to the question of Andrea, the L and K here are linked to the fact that this system, that this set here is actually affine. Okay, so when you have two players, these polynomials here, they become linear functions essentially, and these sets become affine. So how do we get about finding A? Our aim is to find a polynomial path, right? This is in quotes because we're not going to be able to find exactly a polynomial path, and I'll tell you why in a minute. That starts at sigma and ends at an interior point of P sigma, okay? The coefficients that define this polynomial path will define the LPS of each player. And how this is going to how this is going to happen, the coefficient of the term of I degree of this polynomial is going to be the ith order element of the LPS profile we are looking for, okay? And what's the property that we're going to use to find this polynomial path? The property is that the set is semi-algebraic, okay? So defined by a finite union of a finite system of polynomial equations and inequalities, okay? So we're going to prove a quantitative version of a known theorem called the Nash curve selection lemma in order to obtain these kinds of paths. So the lemma we're going to prove says that if P is a semi-algebraic subset of an Euclidean space defined by polynomials with degrees bounded by D, and if we pick a point in the closure of this semi-algebraic set, then there exists an epsilon and a power series such that the image of from 0 to epsilon is inside P. The path starts at the fixed point X that we start at the beginning, and the order of this power series is less than a certain quantity that depends on kappa and D, okay, only. So how we're going to use this lemma? We apply this lemma to the point sigma, or perfect equilibrium that we fix at the beginning, and the closure of P sigma, and we take a power series selection phi. And we obtain a characterization for perfect equilibrium in terms of these selections. Sigma is a perfect equilibrium if and only if there exists a power series path with these properties. And our candidate for L is going to be then the order of the power series, okay? All right, so how do we go about finding K? So we recall we want to find K weakly larger than L such that if sigma is the best reply against phi of order K, then sigma is perfect, okay? So we're going to take that selection phi that we obtained from our lemma, and we're going to plug it into the pay of these different polynomials here, right? These are polynomials, we plug a power series in them, so this is a power series. In the two-player case, it's very easy to see, to compute what this power series actually looks like. In the n-player case, is also simple, but we need a bit more notation. And these are the coefficients of the power series, right? So the pay of differences evaluated exactly at the coefficients of the selection, which are our candidate for the LPS. So we obtain a certain characterization for the condition of lexicographic best reply in terms of the polynomials that are obtained from truncating this power series, right? So this characterization reads, sigma is a lexicographic best reply of order k against whole minus n, if and only if the truncated power series at the order k has a positive sign, essentially, okay? And it's not hard to see why this would be true, because if the polynomial has positive sign, right, then this can only happen if, that this happens if and only if the first coefficient of this polynomial is positive, or the first coefficient of this polynomial is 0 and the second coefficient is positive, and so on and so forth. So you can see from that how the lexicographic ordering operates, right? So you can translate a statement about lexicographic best replies in terms of a statement of the sign of certain polynomials around 0, okay? And so and so the question becomes essentially on whether it's possible to know the sign of this power series around 0 for large enough k. If there exists a k such that we can only see finitely many terms, finitely many coefficients of this power series to determine the sign. And that's where the result of Kurjik and Spochiesa enters in this. There are a few more details, of course, to prove this, but we use the Loyasevic inequality to obtain this, this k, essentially. And that's it. Thank you very much.
Thanks for the presentation. So, are there more questions? Elon, do you want to ask your question again?
Yeah.
I have a question still.
Yep.
So you are using this power series.
Mm-hmm.
I'm wondering, is there a formal relationship between the power series that you're using and non-standard probabilities? So the non-standard analysis of Robinson, where you're assuming an infinitesimal.
Yeah, yeah. So these are so the idea. Well, in the field of rational functions, right? You can provide an order to this field of rational functions and then talk formally about infinitesimals in this field, right? It's not the construction of hyperreals by any sense, but there is a formal way to talking about infinitesimals there, and you're, let's say, leveraging this way of talking about infinitesimals to avoid taking limits, talking in a finite way about infinitesimals. Yeah. Yeah. So if
I also have a question.
Yep.
So when in two-player games, the sequences that approach that's perfect equilibrium are confined to a cone of linear things where you have a clear direction, and that's why it's very easy to find this infinitely many steps. But if you have multiple players, then you can have cusps where it's very hard to sort of...
Exactly. Yeah, you have singularities.
Your curves, I mean, represent that you find a curve that goes into the cusp. Is that what the intuition between this curve selection?
Yeah, so first, so this goes back to how we construct the selection there. So if you look at the set, let me go back to the set here, P sigma, right? If we look at the set P sigma, that's where the cusps are essentially are going to appear at sigma, right? That's what so what you do is to use some tools of resolution of singularities, right? These cusps are essentially singularities, and you can find the Puiseux series, right? To solve as a solution of certain systems, and then you reparameterize those Puiseux series to find the analytic paths that you would like. So that's sort of the idea, right? If you have, as you said, if this is a cone, these polynomials are affine functions, right? They are very well defined. You can take these selections as affine functions, but when they are not, it's a bit more complicated, and you have to use these tools from resolution of singularities.
Also, in the example that you gave, I mean, if you eliminate the first, you had this perfect equilibrium in the middle.
Mm-hmm.
But if you eliminated the top and the left column, it's no longer perfect because it's dominated by right and bottom as far as I can tell. And so you need this top left pair to actually
Mm-hmm.
help the perfectness. So it's probably not a proper equilibrium, this would be my guess. But I mean, anyhow. Yeah.
Oh, the MC, exactly, yeah. So the proper is the BR.
Yeah.
Right? Yeah, exactly. Yeah.
Okay, thanks, Luca, for your presentation and for the questions. So we need to take to stop there if we want to be on time. So we take 4-5 minutes and then we will continue with the presentation.